Welcome everyone. Welcome to the SCUDEM challenge of today. Today's program is gonna be the mechanics of suction feeding. We want to show our regards to Professor Igor Bayata and Masby Community College. My team members for today are JC Okochi, Gift Kripo, and Matthew Shurin. Overview: explaining our problem. Secondly, simplifying the problem. Thirdly, derivations of mathematical models. And fourth, analysis and interpretation of results. Explanations of the problem. A common feeding method for a predatory fish is to quickly open its mouth before sucking in water on prey animals. The resulting physics to model this phenomenon can be quite complicated. Prior to a large scale of investigations of the full dynamics, a preliminary examination of the potential forces that could possibly occur should be conducted. Thus, our problem concerned the development of a mathematical model to mimic the movement of the jaw of the fish. Simplifying the problem, assuming that the mouth parts have simple attachment points at their ends, and ignoring interactions with the fluid as per as our challenge instructions. The resulting model is illustrated to the left of the text.
Derivation of our mathematical model. We chose to base our model on the data provided by Stephen W. Day and his colleagues on the goldfish in their paper on the mechanics of suction feeding in fishes. The graph to the left of this text displays the goldfish's characteristic temporal pattern of suction feeding. As you can see in blue, we have the gape size against time. Modeling an equation for our angle theta between the mouth parts as a function of time, the features of the graph of gape size against time t for the goldfish show a virtually signed progression of gape size g with the time t between t equal to 0 and t equal to 0.1 seconds. When g is equal to its maximum value of 13.75 millimeters, angle theta approaches its maximum of pi radians at a time t equal to 0.05 seconds. When angle theta is equal to its minimum value, which we approximated to 0 radians, time t is equal to 0. And note that the only other possible time that theta equals its minimum is when t is equal to 0.1 seconds. This implies that theta is equal to the maximum value of theta sine omega t, which we found to be theta equal to pi sine 10 pi t. According to Newton's second law of motion, force is equal to mass times acceleration. In the context of circular motion, this becomes centripetal force is equal to mass multiplied by radius times omega squared. In the context of the model we are developing for the movement of the fish's mouth, this equation becomes centripetal force is equal to mass of the fish's mouth parts multiplied by the length of the jaw times the first derivative of the function theta squared. The net force acting on the mouth parts of the fish is equivalent to the difference between the centripetal force and the force of friction. We found the force of friction to be equal to the coefficient of friction multiplied by the normal force acting at the attachment points. We found that this implied the force of friction was equal to 0.3 multiplied by mg sine pi over 2 minus theta over 2. Therefore, the net force was equal to our equation for centripetal force minus our equation for the force of friction.
Assumptions. There are many varieties of goldfish. We narrowed our scope by estimating anatomical factors like jaw size from experimental data. We modeled the jaw such that the lengths of the upper and lower mouth parts were identical and did not change. Working off of a theoretical maximum gape size of 13.5 millimeters, we modeled the jaw lengths as 6.75 millimeters each. In addition, we assumed a sinusoidal progression of gape size with time. This graph is periodic over 0.1 seconds. We assumed the fish's mouth opens as fast as it closes. Analysis of results. For the analysis of our functions in terms of time, we plotted several graphs using MATLAB. Here we see theta against time, we see from 0 to 0.1 seconds, theta goes pi radians, and we see that these forces are inversely proportional to theta. Interpretation of results. As the mouth quickly opens, where and when are the forces acting on the mouth parts the greatest? The centripetal force acts towards the simple attachments at the ends of the mouth, and the force of friction acts between the mouth parts at these points. Therefore, the forces acting on the mouth are greatest at the points on either end, where these simply attached parts meet. As for when F net equals F max, that's when time is equal to 0 or time is equal to 0.1 seconds. This, together with illustrated graphs, imply that the forces are at their maximum magnitude when the fish's mouth is closed. What are the potential limitations of this structure? The structure that we use simplifies the model tremendously, ignoring the interactions between the fluid, the predator's mouth parts, as well as the interactions between the anatomical structures of the fish's mouth and head, such as the fish's jaw protrusion, both of which significantly contribute to an accurate model of the fish's jaw movement. Based on the timing, what is the effective range and other limitations of this feeding technique? The effective suction range depends on the speed at which the mouth opens and closes, and because this time interval is short and the length of the fish's jaw is small, the effective suction range of the fish is relatively short. Other limitations include the fish's mouth is small, implying that the size of prey animal it can allow into its mouth is limited. This feeding technique allows for a large volume of water to enter the fish's mouth, meaning that there is less space available for the solid food. Focusing solely on the movement of the mouth, how can your model be adapted in the next steps to create a more accurate representation of the movement of the mouth? In the next steps, we would account for jaw protrusion of the fish's mouth and integrate this into our mathematical approach. We would account for the interaction between the fish's mouth parts and the fluid that the fish is in, such as the drag preventing the motion of the fish's mouth parts and how the flow speed of this fluid varies. Lastly, we would account for the suction of the fish and the forces associated with this. Here are references.
We would like to thank SIMIODE for hosting this competition and allowing us to contest among other students in the field of STEM.
We would also like to thank Massachusetts Bay Community College for giving us the tools to solve our problem,
as well as Igor Baryakhtar for inspiring confidence in us by preparing us for this competition.
Thank you for watching.
Thank you.